Hello. Okay. So just before we start, I want to make an announcement that at noon in this room there will be the annual general meeting, so everyone's invited to come, and lunch will be provided. And now, I want to Michelle Buono, I'm the CAIMS Communications Officer, and it is my great pleasure to introduce Antonio Palacios, who will be giving the first morning talk. So let me say a few words about Antonio, who I've known since I had hair. Lots of hair. Alright, so Antonio got his PhD in 1995 from Arizona State University with Dieter Armbruster, and then went on to the University of Houston as a postdoc to work with Michael Gorman and Marty Golovinsky, and eventually landed a job at San Diego State University in 1999, became full professor in 2008. He's been collaborating with lots of people, especially the people there at Scalewar, and he's got lots of collaborations going on. He's got 15 US patents. He's working, his work will be on, his talk will be on complex networks connecting invariant bifurcation theory with engineering applications. So, there you go.
Thank you, Luciano. Thank you, everybody, for the opportunity to be here. It's a great pleasure and honor. So, since 1999, I dedicated most of my time to do translational research work where we start with the conceptualization of new ideas and techniques based on dynamical system theory, in particular symmetry, equivariant bifurcation theory, to conceptualize, model, simulate, analyze, design, fabricate, and even deploy some technologies of critical importance. So essentially the full life cycle of a product. So today I'll walk you through two applications. One where it's a continuation of the work that I did with Luciano back in 1999 on heteroclinic cycles. So we use heteroclinic cycles to develop a new novel technology of sensors, magnetic, electric fields, and now we extended the work essentially to what we call the MOS system, which is the microcircuit realization of a universal sensor system. Then I'll talk to you about another novel technology that up until 2011 remained classified. It's called the channelizer. We don't know why the DoD decided to declassify the project. I could say that that was one of the crown jewels of the work that I've done over many years. We were really proud of it. Anyway, so I'll be able to talk to you about it now because we now have a publication out. And then I will finish with the second part with a continuation of some of the work that I did just very recently on gyroscopes with Luciano. So in terms of the gyroscopes works, we put the gyroscopes within the frame of Hamiltonian systems, and that led to new questions that still remain to be answered about networks of Hamiltonian systems. But let me start first with some of the acknowledgments of collaborators, people that I had the pleasure to meet throughout the years. My group at the Space and Naval Warfare Center in San Diego. My main collaborator is Radin, Andy Cole. They're all experimentalists from Georgia Tech. Sukeirone, he went on to the Kyoto University. Joseph Neff, another one from Georgia Tech. Patrick Logini was my first PhD student, and he got hired upon completion of his thesis in 2005. And I always made the joke that he earns almost twice as much as what I earned at the university. But life is not fair sometimes, right? But I'm very happy that he's doing very well. And then a few other members of the group. Professor Hikihara from Kyoto University, that's the person that we're working on the gyroscope systems. And you already met Luciano. So where my skills on equivariant bifurcation theory end, that's pretty much where the skills of Luciano start, and so he's been a great contributor to most of the recent works. We interacted with the group in Catania many years ago when we were trying to develop a ferroelectric version of the sensors. And we also interacted with a few people from Oak Ridge National Lab. And my friend at San Diego State, Joe Mahaffey, from whom I have learned a great deal about delay in differential equations. But none of the works would have been possible without the active participation of postdocs and students, recent postdocs, Bernard Chan and Jose Ray from Brazil. These are some of the students, masters and PhD students that I had the pleasure to work with over many years. 2015, Susan was recognized as the Scientist of the Year by the Undersecretary of the Department of Defense for some of the work that we did on networks of superconducting devices. Mayra Hernandez, she was the first Mexican-American in the Department of Mathematics to ever earn the Graduate Research Fellowship from National Science Foundation. She's now in the PhD program at the University of Washington. And I'd like to also acknowledge the agencies that provided funding over many years. So in recent years, people have started looking at the dynamics of networks from different standpoints of view, from biology, from chemistry, communication systems, you name it. There's ample examples where network systems actually arise. But there is still, the underlying theory that one can use to study network systems still under development. And the translation of those network systems into actual devices, it's even less well understood. So in 2000, let me show you this picture here. 2000, we started working on these arrays of these are Van der Pol oscillators. So the Van der Pol oscillators form a chain, and they are used for communications, radar, and antenna systems. So they are attached to the antenna, and the antenna has to actually rotate to produce a scanning beam that scans the air. That's how the communication systems normally work. The problem is that these systems are subject to mechanical failures. So the group that I was working with, they had figured out that by applying small perturbations to the end chains of the antenna, one could actually produce a beam that we could steer. That became known as the beam steering problem. So we could actually rotate the beam without having to rotate the mechanical antenna from 0 to 180 degrees. So the next problem, the next question was, well, is there a way that we can figure out how we can manipulate not just the direction of radiation, but also the frequency of oscillation? Because these antennas are limited to a certain bandwidth of oscillations of frequency. So the question is, can we do a multi-purpose antenna so that we can actually also change the frequency on the fly without having to change to a different antenna? And so we started working on that problem, came up with some ideas. Then the war in Iraq started in 2001, and so I was invited to participate on a project. It became evident that there was a great need to develop a new novel sensing technology for identifying IEDs, improvised explosive devices. So I was asked if I was interested in participating in the project, and I said, well, sure, except there is one problem. I said, what's that? I said, well, I don't know anything about sensors. I'm a mathematician, so I don't know how sensors work. I said, don't worry about it, we'll teach you. But we need you to think outside the box and help us develop a new novel sensor technology that can be miniaturized. It will require low power. It will be ultra sensitive, more sensitive than what is currently available, and that it would cost actually a minimum amount of money. and that it could be actually disposable so that special forces can carry those along, dispose the sensors, detect the presence of IEDs, and then forget about it. So that's one of the technologies that I will talk to you about it. Then we started also later in 2007 looking at networks of gyroscopes with hydral symmetry and then with cyclic symmetry as well. This is the work that Susan and I conducted around 2009. So these are networks of superconducting quantum interference devices that are called SQUIDs. And they were used to develop, basically to declutter most of the communication systems for the next generation of stealth ships. And so this is the actual size that you can compare of the miniaturized chip. Somewhere in between 2007 and 2009, we were approached by another funding agency, and the technology, the sensor technology was already maturing enough, and they asked us, can you actually use your sensors to sense radio frequency signals? We want to be able to listen to anybody, anywhere in the world that is using radio frequency radio. And we already knew the answer. We say, yes, it's possible. And that's the channelizer project that I'll talk to you later on. In 2005 or 2007, I believe, Albert Furr and Peter Gerber, they won the Nobel Prize in Physics for the discovery of the giant magnetic resistance effect. That's the change in resistance of certain materials under the presence of magnetization. So they conjectured that the spin of the electron could also produce a microwave signal. So the problem is that in 2009, the first experiment was conducted at Army Research Labs. They measured about 250 picowatts of energy coming off of the spin of one single nanobot. That's too small for any practical applications. So in one of the seminal papers from Albert Furr, he predicted, or conjectured more than anything, that it might be possible to create networks of nano oscillators so that the collective synchronization of many of them could be used to increase power. The problem is that nobody had actually been able to figure out how to synchronize them. There were some experiments conducted at NIST, National Institute of Standards and Technologies, and they were able to synchronize two, but just synchronizing two was rather difficult. And the problem was that the analysis of the network was very, very complicated. And that's one problem that we didn't tackle until the beginning of this year. We finally got a publication, and again, it was thanks to the contribution from Luciano. Then we extended some of the work to energy harvesting systems, and more recently, to networks of coupled oscillators for precision timing devices. So let me take you back to 2002 and talk a little bit about the sensors. So let's put things into context. So this is just a standard definition of a network system. So we have the state variable of 8 nodes connected. Each node, we're assuming that they're homogeneous for right now. They're sitting in a vector space in Rn. So the network dynamics is defined by this vector field. Little f represents the internal dynamics of each individual node, and h is the coupling function that defines how the networks are coupled. So this is just one formulation, although nowadays we know that there is even a much better formulation in terms of monoids that allows us to represent the network in a more efficient way, in the sense that it can be used to discover unfamiliar bifurcations in the network system. But I won't have time to talk to you about that. So let me tell you first the work in 2000 that was published with Luciano and Marty on heteroclinic cycles. So a heteroclinic cycles is essentially a collection of trajectories that forward in time go to one invariant set and backward in time go to another invariant set. The invariant sets could be equilibrium points, periodic solutions, or even chaotic sets. So this is the famous Guggenheimer-Hall cycle. One way that we can identify the presence of heteroclinic cycles, although it is not a necessary and sufficient condition, is through the lattice of isotropy subgroup. So at the top level, so over here is the main group of symmetry, big gamma. So sigma 1, sigma 2, these are the isotropy subgroups that define the amount of symmetry of each individual solution. So think about this could be an equilibrium, a periodic solution, another periodic solution, and so on. And this next layer corresponds to another set of invariant subspaces. The idea is that the dimension of the fixed points of space of this layer, the fixed points of space, is the space where the group essentially acts trivially, is 1. So basically the solution sits in terms of the reduced equations in a one-dimensional manifold, and here the dimension of the fixed points of space is 2. So essentially what this says is that these invariant subspaces are the manifolds that allow for the connections from one solution to the next through essentially saddle sync connections, and that way we can traverse the lattice until we're back to a conjugate or the same individual solution. That's how we can identify the presence of a heteroclinic cycle. And so we studied systems with dihedral symmetry, and we were able to prove the presence of cycles involving steady states and periodic solutions. Here's the actual simulations of the original network dynamics. This is for the reduced normal forms. Without getting into the actual details, one of the things that eventually came to be one of the keys for developing the channelizer is this section right here. So doing the analysis, without getting into the actual details, one can show that the isotropy subgroup symmetry essentially forces certain cells, in this particular case, node number 3, to oscillate at twice the frequency of the other cells. So that's just an inherent behavior of the network dynamics. So right here with I zoom, I don't have the larger picture, maybe I So this is the normal form, the network equations. We can show that at the bifurcation point, certain cells here are oscillating at a higher frequency. So just keep that in mind for later on. So we were finishing the work, and I remember this is another thought. We're walking with Marty and Luciano to the faculty lounge, and I asked Marty, so what would happen? I wonder what would happen if we add delay to the network equation. And he looked at me like really surprised, and he asked me, why would you want to do that? And so I gave it the best possible answer that I could find at the moment. I said, I don't know. So it took me about 5-7 years to have a better answer. So I'll tell you about how critical the delay is a little bit later on. So this is how most sensors, magnetic, electric fields, many of the sensor technologies are based on essentially, if you talk to the engineers or the physicists, there is a potential function that describes the dynamics of the ferromagnetic or the electric materials. H is what the engineers call the biasing signal. It's essentially the energy that you apply to the system. So when H is equal to 0, the potential is symmetric, and the minima correspond to the two different magnetization states of the system. Think about a -1 and 1. So with that energy, the system will not oscillate. So you apply H, and then you start rocking the energy function, so the system starts to oscillate back and forth. So then, to detect this is without any external field, then you put the magnetic sensor, for instance, under the presence of a magnetic field. So without the magnetic field, the power spectrum decomposition is the main frequency and the odd harmonics. When you put the magnetic field and the first even harmonic appears, and that's usually the one that is used as the detector of the external field. Very simple detection mechanism. The problem is that in actual application, that will require the computation of the fast Fourier transform or any other technique to calculate power spectrum decomposition. And that tends to be very expensive and time consuming. So we came up with a different idea. And this is called the RTD, or residence times detection. So the idea was the following. We thought about it and said, well, how can we improve energy consumption? And I remember that, you know, if you look at all of the papers on coupled cell systems networks, there is this concept of self-induced or coupling-induced oscillations. So, well, how about if we were to couple these systems, create a network, and then just require a minimum amount of energy to keep the system out of the steady state, so that it starts to oscillate almost on its own with very minimum amount of energy. So that came to be one of the ideas to reduce energy consumption. The next idea is, okay, so if I create a network, would it be possible to create a heteroclinic cycle through the network, through the oscillations? And the question is, obviously, why would you want to do that? Why would you want to have a heteroclinic cycle? Well, because the families of periodic solutions that accompany the cycle at birth have an infinite period, right? So there's an infinite period bifurcation. So I thought about the idea that instead of computing the power spectrum decomposition, we could look at the symmetry breaking effect of an external field on the top to bottom symmetry of the oscillatory wave. And then we measure either the difference in times or the ratio of the differences in crossing times. And that came to be the new RTD detection. So we started looking at flux-scale magnetometers, because they're very, very simple to construct. So a flux-scale magnetometer is made of a ferromagnetic material, like this one right here, and it has two coils. In one coil, you excite the system into saturation, you create a hysteresis loop, and then you induce the oscillation. So one coil is the excitation coil, the other coil is the pickup coil, where you pick up the actual oscillation. Ferromagnetic materials behave into two different states. So above the crib temperature, at the atomic speed, at the atomic level, the magnetization speeds are all non-uniformly aligned. Then below the magnetization, below the crib temperature, they become into either aligned in the one direction or the opposite. So this is called the paramagnetic state, this is called the ferromagnetic state, up or down. This is the state where we want to have the system operate. This is the hysteresis loop, +1, -1, that's the potential function that describes the system. So the dynamics, you know, again, we go into the mean field approximation. So we approximate, we take the average of the magnetization speeds, and we can show that after certain simplifications, this is the potential function that defines the system, and this is the dynamics of the equation. Without a hyperbolic tangent, the system simply dies out into the zero equilibrium. So the hyperbolic tangent is just simply the activation function that controls the output of the system upon the input of the system. So this is the external field that one would like to detect. So if you look at this equation, if you notice the equation is essentially the same as the version of a hot field neuron. There's, you know, that's the, you know, at the higher level, you know, this has nothing to do obviously with neurons, yet there is a very strong similarity. So this is the coupled system. So this is the full equation for the case of unidirectional couple. So now we're going to take n of these ferromagnetic materials, we're going to control the courier temperature. Lambda is the coupling parameter. So the coupling comes through magnetic flux. One of the things that I learned over the years of working with engineers is that not every coupling function can be implemented in the actual realization of the device. In this case, bidirectional coupling is very complicated. It's not impossible, but it's very complicated because you have to direct the magnetic flux and then send it back again in the same direction. And that imposes a lot of complications in the system. Era is the contamination of the signal. So we looked at all the effects of noise, effects of noise coming from the electronics, color noise. Epsilon is the external signal that we want to detect. Tau is the delay that we added into the system. And this signing here came actually by accident. So, so just keep this sign in mind. I'll tell you exactly what happened. So this is the bifurcation diagram. Let me enlarge this a little bit. So about a certain threshold of critical value of lambda, the system doesn't oscillate. So right here is the birth of the heteroclinic cycle, and then this is the family of limit cycle oscillations that accompany the cycle. We want to operate the device in this region as close as possible because that's where the oscillation have the longest period. That's where the symmetry breaking effects are very, very high, and that's where we can actually increase sensitivity. So to give you an idea, back in 2002, the best you could do with a flux gauge magnetometer was to measure about 250 microteslas. So if we zoom in here, we see that there is biostability. There is a branch of steady state solutions that comes from this other branch right here. So the problem is that when you turn on the sensor, you have no control of the initial conditions. So we can do that easily mathematically, but in practice, setting up those initial conditions is very complicated. So that's where delay comes into play a little bit later. So that's the bifurcation diagram. This is the actual phase space visualization. So this is the actual heteroclinic cycle, and these are the families of periodic oscillations. This is going from right to left. And over here is the first generation of a coupled network of flux gauge magnetometers. Normally, you would put at one end the actual energy, the biasing signal. So notice that there is no energy, there is only cables. Eventually, we measure and we calculated about 1 foot of cable translates into 1 nanosecond of delay in the coupling circuitry. And this is the actual coupling circuitry where we apply just a small amount of excitation into the system to get it started. So one day, we were able to show that we could increase sensitivity, and the best we got was somewhere around 100 picoteslas. So we went from 250 microteslas to about 100 picoteslas. So one day, so the question is, what happens if you increase N? So if you go from 3 to 4 to 5. Well, first there is a theorem that we prove that you have to have an odd number of oscillators with the Zn symmetry in order to get oscillations. There is no oscillations with N even. So one day, we didn't observe any change in sensitivity in going from 3 to 5, 7. But one day, one of the engineers, by accident, flipped the orientation of one of the sensors without noticing. And then all of a sudden, we started to see an increase in sensitivity. So we went back to the model. We didn't know why that was the case. And we added the -1 term. That's the one that corresponds to the flipping of the orientation. We call that the alternating orientation of the network, and we showed that in that case sensitivity increases linearly as a linear function of the actual number of sensors. Let me back up a little bit. So when we add delay, we notice that when we added delay into the system, delay tended to, when we power up the sensor, it was almost, most of the times, it was almost oscillating. So when we did the analysis, that's where I got the help from John Mahaffey. We did the analysis, including delay, and we found an optimal value of the delay. From the bifurcation diagram, added delay into the system pushes the location of this half bifurcation towards the right, and the onset of the heteroclinic cycle to the opposite side. That was great news, because that means that once that we operate the device right here, the device will always be oscillating. So we actually integrated delay into the microcircuit realization. And this is one of the papers that we published. Geometrically, the effect of delay here, a small delay, anything that is inside this pyramidal region, is actually the basin of attraction of the branch of the steady state that I showed you previously. Anything that is outside goes into the oscillations. As we increase the effects of delay, the basins of attraction of the steady state starts to shrink. So this is the actual sort of the first test. Very close to the heteroclinic cycle. Notice that the oscillation basically, this is a heteroclinic cycle. In the simulations in MATLAB, this is the simulations in the oscilloscope. They match very well. With that, the alternating orientation near the onset, although sensitivity increases, it remains constant for any value of n. But when we do the alternating orientation, sensitivity increases linearly as a function of n. So then we went out and tested the sensor on the ground at Camp Pendleton. Then we wanted to do the testing underwater. And so we were working together with one of the Navy SEALs teams in San Diego. And we asked them, we would like to scatter the sensors in the San Diego Bay and have a swimmer swim by carrying some type of ferromagnetic material simulating an IED. Can we do that test? But we need a couple of swimmers that can actually swim really fast, and I can actually get very close to the sensor so that we could measure not just sensitivity, but also resolution. Resolution in terms of how far can the sensor detect the signal, how quickly it will respond. So they told us yes, but it was going to cost you some money. So we have to pay them off of the grant. Said as long as you fit well the swimmers, they will perform any task that you ask. So we got two dolphins from the Marine Mammal Program in Spainward. So we attached some ferromagnetic materials. This is the testing facility. We basically used about 7 of them. This is the 5th generation of the sensor device. This one was done just with 2 networks, one as a backup. Now we have hundreds of them. The actual measurements is about 5 millimeters by 5 millimeters for the sensor device. And this is the actual response. So every time the dolphin passed by, the sensor picked up the signal. So sensitivity went up to about 200, about 100 picoteslas. And finally, it was just a few months later, was the deployment in Iraq. So after the years, eventually, the Navy, DOD, didn't have any more use for the sensors. We begged them for 6.3 level funding so that we could translate the technology into other practical applications like biomedical applications, but we were denied always the funding. So eventually what we did, we created our own company. It's called IMF Microsensors. And so the first product that we're developing is, now this is a sensor that uses the same ideas, but to detect electrical signals. So we developed the most powerful sensor in the planet. It senses 10 to the minus 15, that's 10 femto amps of electrical current. So it can record an ECG directly without even having contact with the skin. And that's one of the products that we're trying to develop in recent years. So let me take you now to the work on the channelizer. So without getting into any questions, let's just play around with symmetry. And let's see what happens. Suppose that you have two arrays. In one array you have, we have the dynamics x1 to xn, the other one is y. And they're coupled somehow. So let's suppose that the x array oscillates in a traveling wave pattern, right? 2 pi divided by a. And the other array oscillates in phase. There is no phase shift from one to the next one. Well, we can show that under this amount of symmetry in the system, the traveling wave remains fixed, but the in phase starts to oscillate 8 times faster. This came again from the idea of the work that we had done, what we had observed with the heteroclinic cycles, where DN symmetry forced one of the networks, one of the nodes, to oscillate faster. In this case, it's the entire array. So that's frequency of conversion. So here is the actual electronic realization for the case of n equals 3. So traveling wave in phase, and the traveling wave oscillates indeed 3 times faster. The equations, it doesn't really matter. You can do this with Van der Pol, Dauphin oscillators, Colpitts oscillators, any type of nonlinear oscillator. Now let's go the opposite direction. So now let's suppose that we have n of these arrays. So we have one array oscillates in a traveling wave, and the other array again in a traveling wave. And if we continue going through what we call this a cascade array, although I think this will actually fall more within the category of a feed-forward network. So if we do the same analysis, we can show that the traveling wave here has to, in order to remain fixed by the symmetry of the cyclic oscillations, of the cyclic rotations, x1 must be x1 of t plus n plus 1 over 3. Since x1 is t periodic, then n plus 1 must be a multiple of 3. So that for any integer. So for instance, when n is equal to 5, that means that x2 will oscillate at 1/5 of the frequency. And we can do all the combinatorics and increase the number of nodes, increase the number of arrays, and we can actually play around with changing frequencies. This is the actual circuit realization on the left with n equals 3, and this is a 1/5 frequency down conversion from 180 to about 37 hertz. This is the actual network equations if you're interested. IC is the current that controls the amount of coupling. This is the external signal. This is the radio frequency that the sponsor wanted us to detect. And this is the dynamics of the next array. So this is the actual bifurcation diagrams that shows you the regions where you get the 1/2, 1/5 frequency down conversion. And this is the channelizer. So the idea was to create various channels of these networks of oscillators. Here is the radio frequency signal that comes from some antenna. So if somebody is communicating with somebody else at one frequency and then they switch to a higher frequency, the channelizer is able to pick up all those possible frequencies. Changing the IC component basically shift the system from one Arnold tone to the next Arnold tone. So the system can actually lock into a signal. This is the actual circuit realization. This is the different channels for different values of IC. So IC controls the actual frequency location of the Arnold tones, and the IG parameter basically opens or closes the channel in order to filter out noise, or if there are multiple signals coming in at the same time. So I have about 20 minutes, and so in 20 minutes I'll just talk to you now about this other technology. This one is not mature yet. We're still in the phase of, well, we completed the analysis, we know what happens in the system. Now we need somebody to actually do the experimental work for us. This is the network of gyroscopes. And so essentially a gyroscope, the way it works is as follows. A gyroscope is used to detect angles of rotation. It works on the basis of Coriolis force. So when the gyroscope is made up of essentially two mass spring systems. So let's call one axis the driving axis and the other one the sensing axis. So I can't see from here which one is which, but let's say this is the driving axis. So in one direction I excite the gyroscope and it starts to oscillate. So if the entire system is not rotating like your cell phones, when the cell phone is not rotating, there is no Coriolis force on the system. So the sensing axis remains quiet, remains in a steady state. And then as soon as you start applying a rotation, there is a transfer of energy from the driving to the sensing axis, and the oscillations in the sensing axis are proportional to the amount of angular rotation. So what we observed through simulations for the case of bidirectionally coupled is that there is a threshold value right here, and if you look at the scale, this is very, very small, but on one side, it's almost a vertical line. On one side of the bifurcation parameter space, there are no oscillations. On the other side, there are oscillations, and they are actually in train, synchronized. So this is the actual bifurcation diagram that shows how the system goes into synchronization. In this case, synchronization is important because over the years, a gyroscope degrades based on imperfections of materials, noise, so the gyroscope starts to drift. And that's what people measure the robustness of gyroscopes. How much do they deviate in the angle of detection over units of time? So we simulated and we found somewhere around n equals 8, and this is something that we still don't know why, but somewhere around n equals 8, phase drift becomes very, very small. Then it increases again. So we would like to develop a network of coupled gyroscopes that will operate in this region. The equations are just very, very simple. But when you put it into a network system, it becomes high dimensional. So this is, if you look at just the left-hand side, just a Dolphin oscillator, the cubic is all linear, and there's only just the cubic here. This is the driving force that drives one of the axes. This is Coriolis force, and this is the actual coupling circuitry. In the case of the gyroscopes, the latest version of the implementation calls for two layers. In one layer, the MEMS version of the gyroscopes, these are micro-mechanical devices, and on the top will be the layer that will do the actual coupling so that it could be reconfigurable.
So for your gyroscopes, are they all aligned? Like when you have a network, is the driving axis all parallel?
No, they're not necessarily aligned. Yeah, they're not necessarily aligned. You can actually place them in, you know, for all that matters is just the connectivity from one sensor to the other. So we introduced the, so what we realized is that we could actually treat the gyroscopes as a small perturbation of the Hamiltonian systems. So we can cast the equations that I just showed you in Hamiltonian form with the small forcing term added as a perturbation of the Hamiltonian. And then we look at the actual cell configuration, the internal dynamics, the Hamiltonian coupling that comes from one node to the next one. This is for unidirectional, then bidirectional, and then the actual forcing term. So we did the analysis. We have a network of n of n. We can show that in the case of dn acts in this form. It's just a simple exercise in linear algebra. And then we define, using the tensor products, we define the action of this is the 2 pi divided by n rotation, and this is the reflection in dn. So we have two groups that act on the gyroscopes. One is the cyclic rotations for unidirectional, dihedral for bidirectional, and Z2 minus I is the reflectional symmetry in the internal dynamics of each of the gyroscopes. So then we introduce the symplectic formulation, define the entire system as a Hamiltonian system in this form. And for the network, we define the symplectic structure as n copies of J4. So then the question that we immediately came to the problem was that special symmetry is not a necessary and sufficient condition for the network to retain the Hamiltonian structure. In a follow-up manuscript to the one that we did to describe the dynamics, we developed some topological tools to test whether the network will remain Hamiltonian or not. And so essentially we found out that the unidirectional coupling will not retain the Hamiltonian structure, whereas the bidirectional will retain the Hamiltonian structure. And the proof is just essentially by brute force in this case to show that the Hamiltonian, the matrices that are associated with the unidirectional are no longer Hamiltonian. So now this is the case where we have no forcing, and this is the case where we have forcing. So the work basically consisted of two main theorems. In one theorem, we proved the one-to-one correspondence between solutions of the unforced system to the periodic oscillations of the forced system. So if the forcing parameter here is rather small, and we have bidirectional couple, then the synchronized 2 pi over omega periodic solutions near the trivial equilibrium with isotropy subgroup will be linearly stable for lambda bigger than this value. This came from the actual linearization using the reducible representation of Dn. So the proof consists of 3 steps. Establish the relation among solutions, study the spectrum, and derive the normal form. I don't know how much time I have left, about maybe 15 minutes. I'll try to just walk you through the main ideas. 10 minutes. Okay, well, thank you for letting me know. This is the first proposition that if we have an equilibrium of the unperturbed system with this amount of symmetry, then the periodic solution also preserves the same symmetry group. And the second part says that the spectral stability properties from the unperturbed to the perturbed system are preserved. So I'll skip the proof. That's just based on a point array map. And so this is the isotypic decomposition. Essentially, without going through all these details, all we do here is just find the right basis to diagonalize the matrices of the coupled system. So we have 2 diagonalizations for n odd and n even. This block, that's the one that contains the bifurcations for n odd, and this is the block that contains the bifurcation for n even. Since each of these matrices is Hamiltonian, then we can multiply, there should be a matrix J times n, J times S equals n, and then we solve for S, and then we just rewrite the basis in this form. And once that we have that form, we can compute the actual Hamiltonian function for both cases, n odd and n even. And the previous theorem, the first theorem, basically by computing the eigenvalues of the critical blocks, we can show that right here the system is, so if this is less than lambda star, or lambda critical, we have positive and negative real eigenvalues. The system is unstable and it's spectrally stable, meaning that all the eigenvalues lie on the purely imaginary x's for lambda to the right of lambda star. So what this means is that if you remember the picture of the bifurcation diagram, this means that we are on the side of the entrainment region of the bifurcation. So then we find another change of basis to write the linear matrices in normal forms, and again we repeat that for n odd, n even, recompute the Hamiltonian, and then we go into the nonlinear normal forms. That's where things start to get a little bit nasty. So the Hamiltonian also has to remain invariance under the action of the Tn curves, and that allows us to rewrite the actions of the cyclic rotations and the reflections for Dn, and then we find a new basis and we introduce, we complexify the variables, and then we have again the final action from where we can derive all the invariants for the Hamiltonian function. And then we just go through the actual tedious exercise where we show that all of the invariants, these are the generators for the invariance of the Hamiltonian function. And this is the second theorem that tells us how the bifurcations occur. So we have a Z2 minus 1 orbit. These are the branches of periodic solutions that bifurcate with an isotropy subgroup Z2 kappa when lambda is to the right of, to the left of lambda critical. So for n odd, we have, this is the actual form of the traveling wave. For n even is this. So if you just set n equals 3, let's say n equals 3 for n odd, we can show that if you do the permutations here, if you put j equals 2, n3, z2 equals z3. When n is even, let's do 4. So that will show 1 equals 3, 2 equals 4. So that means that two gyroscopes are synchronized, these other two are synchronized, but they're out of phase by half a period with respect to each other. So this theorem tells you exactly the patterns of oscillations that will occur as they come into the synchronization regime. So let me show you the diagram. This is just the equivariant splitting lemma to focus mainly on the non-degenerate terms that define the bifurcation. Let me just show you the actual results. So this is the case of n equals 3. Remember, we found 1 and 3 to be the same, 1 and 2, 2 and 3. 2 and 3, and then this is the conjugate. As they come close to the bifurcation point, they all become fully synchronized. N equals 4 is 1 and 3, 2 and 4, so 1 and 3, 2 and 4. And then the conjugate, and then as we increase the coupling strength, they become fully synchronized. So the analysis allows us to describe not just how the patterns are going to bifurcate into the synchronized regime, but it also gives the engineers that lambda star which is critical, which can be calculated for any network of any size, so that they know exactly where they need to operate the network to obtain the complete synchronization. And this is the actual MEMS realization. So this is the layer of what you see in here in each of these units. This is a 3x3 matrix of gyroscopes. So the idea is at the top there will be a second layer that will actually do the connectivity. so we can actually create any type of coupling structure. So these are some of the patents that have been published over the years. And these are some of the, I run out of time, so, but these are some of the other projects that we've been working on in recent years. I just wanted to point out one fact, that despite the fact that we have, I should probably, withdraw my claim that we have the most sensitive sensor in the planet. Sharks are 400 times more sensitive. They have these cells called ampulla of Lorenzini, and there is a network that we're still trying to understand to see if we can extrapolate the connectivity of that network to develop an even better sensitive device. And this is the actual application that Shannon talked to you about the other day on precision timing devices. Finally, I don't know if I have connections here, but let me just do this quickly. No, it's not picking it up. That's okay. So I just wanted to point out to you and invite you, we are organizing CAIMS. This is the international conference on applications of nonlinear dynamics in 2018. So it's a conference that we try to bring together people that are doing not just theoretical work, but also experimental work, so that it can actually lead to real applications. Next year, we were approved to go back to Maui. So August 5th through the 8th. So mark your calendars, you're all invited, and I hope to see you there. Thank you so much.
So we have time for a few questions. Yes?
I have a question about your statement about this one particular system not being time. When you are trying to prove something like this, do you assume that you are looking at all possible Poisson tensors, possibly not constant Poisson tensors, but Dynamical Poisson tensors, or you are restricting your claim to only constant Poisson? In other words, canonical Hamiltonian stuff.
Yeah, I think we are restricting ourselves just to the canonical form.
Constant.
Yes, and we assume that, so each of them has its own Hamiltonian function, and then we want to see if when we couple them, whether we retain a Hamiltonian structure for the entire network.
Yes.
Can you take a minute and just refer to your favorite patent on this list of patents?
Oh.
That might be the most interesting one.
So there is another story to that. So let me see if I this one right here, 2012. This is the one that I didn't tell you the story about that since you asked me. I was in a dispute with the university for about a year and a half. I have to hire a lawyer from the Tesla organization. There is a Tesla organization. If you Google it in case you're interested, Tesla.org has nothing to do with the Tesla manufacturer. This is a non-profit organization that was created to protect the intellectual property of people like me, that just a university professor. So most of the work that was done here was done under one of the high security clearances. And so I couldn't talk to my wife about it. I couldn't use any computers at home, much less at the university. It had to be done in a SWIFT room. The Navy basically owns the licensing rights to the patent. And so when we created INF, we bought the license from ourselves. So we entered into a contract for $3 million and predicting that the biosensor could be used for biomedical applications. So one day one of the lawyers from the Spain board, I don't know why, contacted the research foundation at my university. He said, you know, there is a company here that is buying the licenses rights for this patent. One of the inventors listed on the patent is one of your professors. So what is your position on it? And they asked, well, how much are you selling the license for? It says $3 million. I said, we own it. So we went into a dispute, and I have to go through the faculty union, and then eventually we had an arbitration. I hired my lawyer, and essentially what saved me at the end, because I couldn't become part of the company, because then anything that we would do in the company, the university would want to claim ownership also. So I had my notes from the years in Houston, and I had dates on those notes. So I brought my notes to the arbitration, and I showed them that the ideas for the sensor didn't come from the work that I did in San Diego, but actually from the work that I did back in Houston. And then this is when I realized that one of the nodes can actually oscillate at different frequencies. This is when we saw heteroclinic cycles. So if anybody has any claim, so don't tell that to Houston, but if anybody has any claims, it's UH, Los San Diego. And so then this became probably the most favorite patent of all.
Question, the last one?
You're taping these, right?
Very good question, and you know, there's so many things that I didn't have time to discuss. You're essentially asking me about non-homogeneities in the system. It's a very, very good question. That was the work that helped Myra obtain the NSF Graduate Research Fellowship. So she looked at the effects of non-homogeneities in most of the bifurcation analysis. And so we looked at effects of non-homogeneity and also the effects of noise in adding a little bit of noise into the system. So not only we manipulated or exploited delay, but we also added a little bit of noise because there was a little bit of a stochastic resonance. But to answer your question, what Myra found out is that you have about plus to minus 10% variation if you in the homogeneities of the individual nodes. So the variations, by the way, where do they come from in the case of the, let's see if I can. So in the case of the flux gate magnetometers, just imperfections of the ferromagnetic materials. And I didn't tell you that, you know, not all ferromagnetic materials have operate in the ferromagnetic state. In fact, we needed a value, you know, probably means nothing to you, but C equals 3. Anything bigger than 3, we get very, very good validation against the model. The problem is that there were only 2 mines in the world that manufacture ferromagnetic materials that have that characteristic. One is in Romania, and the other one is in another country that didn't give us permission to actually extract it. So we went to Romania to get the wiring to do the action, to get the ferromagnetic material for the very first version. And that's where we started looking into the effects of non-homogeneity, and we calculated that more or less the system is robust enough that even if you have about up to 10% variations, you're still able to preserve the heteroclinic cycle, the bifurcations, a little bit above 10%, which is, you know, it was a very good range. That's when the system starts to degrade.
Okay, so before we thank Antonio, the organizer would like to.
Thank you so much.
Thank you very much.